Hello everyone, this is Dilip. In the last couple of videos, we have seen a great deal about neural networks. In this video, let's see how to build a neural network using Python from scratch. We will not use any third-party libraries like Keras, etc. We will write our own code, which can be easily imported to other languages as well if required. For building the neural network, let's use MNIST data for training as well as testing purpose. So this is a data set of handwritten digits. As we can see, these digits are between 0 and 9. And we are given images of these digits, which are all 28 cross 28 images. So based on the input image, we have to determine what is the number that it represents. So it is guaranteed that it will be between 0 and 9. And those are handwritten digits. So we have to train our neural network to recognize these images. Let's move on. So before we go into doing our neural network, what we'll do is we'll just take a look at all the initial steps that are required to build a neural network. This will be a short one, so we'll just go through the important things so that it will be easier when we look at the code. So this is the hypothesis. This is otherwise referred to as forward propagation. So in this, what we do, we just take whatever the input we get, input features, we multiply with them the weights, and we get this activation neurons. And these activation neurons again will multiply with these weights to get the final hypothesis or the forward propagation result. So this is what we do. So final h of x is nothing but this, whatever the activation neurons in this layer multiplied by the weights, we get the final activation, which is h of x. It can also be called as A12. So for multi-class classification problem, like the one we are dealing now, where we have to determine between 0 and 9, we will have multiple neurons. So whichever neuron has the more weight, that is the classified output we will figure out. Okay. So let's move on. So that is about hypothesis. And this is the cost function. So this is the logistic regression cost function. And from that, we derive the cost function for neural networks. So this cost function we just do for checking purpose. This is not required to be done for our training of neural network. So just for testing of our neural network for some iterations, we'll use this cost function. Next is backpropagation. So once we put initially some random weights into these parameters, then we use backpropagation to update these weights. So for the backpropagation, you already know, like from the we'll first do the hypothesis, and then we calculate the error for the last neuron, like last layer. How many neurons are there for last layer? We calculate the error by subtracting the actual result from the calculated result. So we calculate the error value for these neurons as well. And then what we do is, using the delta values, we get the error gradient for each weight. So we multiply the activation neuron with the error of the next layer. And we have to add the regularization. So that's how we calculate the gradient for each weight. So this is how the backpropagation algorithm works. So initially we initialize all the gradients, whatever we call as delta values, to 0. And then we iterate through all the training samples. And for each training sample, we do forward propagation. to calculate the activation neuron values, and then we calculate the error values, and we'll update the delta values, and then we go for the next training sample. And once we complete all the training samples, what we do is we calculate the gradient. So for calculating the gradient, we also multiply the regulation parameter, which is lambda, with the weights. So for the bias input neuron, or from the activation neuron, whatever the bias is there, for that bias there is no regularization required. So that's why when I not equal to 0, regularization is not required here. So that is how we get the gradient. So once we get the gradient, it is simple. We just use the normal gradient descent, which is nothing but the weights subtracted by learning rate times this gradient. Okay. So since going through all the training samples is costly, what we do is we go through a subset of training samples for each iteration. So that's what we'll use, a stochastic gradient descent, because we take a subset every time and the subset is always different. So this is what we'll do on neural network. We'll calculate the cost function. We'll calculate the back propagation. And then we'll get the gradients and the stochastic gradient descent, because for iterating new training samples, we use stochastic gradient descent. So since we have 28 cross 28 images, so all the MNIST data has each image of size 28 cross 28, and those are all grayscale images, and each you can say each array value, it will be between 0 and 255, because each pixel is between 0 and 255. And since we have 28 cross 28, if we add all of them, it is nothing but 28 by into 28, which is 784 neurons, which is our input features. So once we get the input image, then in the output, we have to classify it between 0 and 9. So we have 10 neurons in the output layer. And in between the hidden layer, we can have any neurons you want. So here I have put 50 neurons in the hidden layer. So this is how our neural network looks like. So 784 neurons in first layer, 50 neurons second layer, and 10 neurons in the output layer. So let's go to the code now. We'll use Google Colab to show neural networks, because this is an easy to use interface for writing the text as well as the code. And you can copy it, reuse it, share it, it's fine. And I'll give the GitHub link as well. Feel free to use it and modify the parameters and try it out for yourself, how the neural networks behaves with the tuning of the parameters. Let's look at how I implemented this. As I already explained, we'll use the MNIST dataset. It will have the handwritten digits between 0 and 9. So first we'll use the third-party TensorFlow API. So we'll use this only for downloading the MNIST data, because this way it is easier. And we'll not use it for actual backpropagation or any other neural network implementation. So this MNIST.load data will load the data. And here itself, we can split the data into training and test data set. And we are also printing how much it has split. So total, there are 70,000 images. So let's just run this. So it has split it this way. In the training data, it has put 60,000 images. In the test data, it has put 10,000 images. Now, since the values are between 0 and 255, to normalize the data, we'll divide by 255 all the elements in the array. As we can see later, this way normalizing the data and making it sure that it stays between 0 and 1 will help us in solving the neural networks or any other machine learning problem faster. And we'll also print the training image. So after dividing with 255.0, so as you can see, it is a set of 28 elements, and each element in turn has 28 elements. So this is a 28, you can just imagine it has 28 rows, and each row has 28 pixels in it. Okay, so this is the first row, this is the second row. Since initially there will be some just normal, nothing will be there, just a white, and then there is the values of the image, the pixel values. Okay, so let's move on. Next, we will define the activation function. As I explained in my last video, there is a relay activation function, softmax activation function, and sigmoid activation function. But for our neural network, we'll only use the sigmoid activation function. So here I have defined them. So quickly, you can take a look at it. I'll just talk about sigmoid activation function. So sigmoid activation function, what it does is, whatever the input value you give it, it will make sure its value stays between 0 and 1. So even if you give positive infinity or negative infinity, it will make sure its value is between 0 and 1. So that is what sigmoid is. So this way, normalizing the values again between 0 and 1, it will help us in our calculations. So that's why whenever we get after multiplying the weights with the activation neurons, what are the values we get, we immediately pass it to the sigmoid activation function. It has two benefits. First benefit is it will normalize it between 0 and 1 so that our calculations will be easier. Second benefit is it will introduce non-linearity. Since our neural networks are linear, like whenever we multiply weights with the neurons, it just looks like a linear function. So this sigmoid will add the non-linearity. So these are the activation function code. So I'm also testing the activation code here. So next we'll look at how okay, so we'll initialize our neural network. We have input features as 28 cross 28, which is 784 input features. We have to add the bias as well. So it will be 785 will be the input. So this is the input layer size I am putting as 785. Hidden layer size, we have taken 50 neurons. Adding the bias neuron, we'll put as 51. And this is the input bias neuron. So since input bias neuron, whatever value is there, we have to give it. I'm initializing it to 0.5. This is because we know that all our pixel values will be between 0 and 1. So I'm just putting an average 0.5 into it. And then I'm using he initialization for initializing the values with random numbers. So what this outputs is, it gives out the random numbers in the Gaussian distribution between 0 and 1. And what we are doing is we are multiplying it with square root of 2 by first layer size. So since these parameters or the weights what we are initializing in GD1 is between first layer and second layer, whatever the first layer is there, 2 by that first layer, which is the input layer here. You just take a square root of it and multiply with this Gaussian distribution. So this is called he initialization. So this he initialization gives us the most accurate input values such that our neural network can converge in a better manner. So more about the problems of whatever I face, I'll talk in the next video. So let's just move on. So after initializing the weights with the he initialization, let's just print some weights. So here you can see the weights are printed here. Now in the back propagation, we need a way to calculate the forward propagation, which is nothing but calculation of hypothesis. So for that, this is a function for it. So what we do is, whatever the image is there, we get a 28 cross 28 image. So we just flatten the image. Flatten the image is nothing but, say you have 28 rows and each row has 28 pixels. So what we'll do is, first 28 pixels you put in one array, and then the 29th element you will take as the second row. So like that, 28 cross 28, we'll have 784 elements in a single array. So from 2D array, we are changing it into a 1D array. So that is what this flatten will do. And after flattening the image, since we have the bias neuron as well, we are just adding the bias neuron, and that will form the input array. And then this is how we are calculating the second layer. So in the second layer, whatever the activation values are there, to calculate them, we have to multiply the weights or the parameters with the input array. So we get the second layer activation, which is NUR1. And after that, we are again doing a sigmoid so that those values stay between 0 and 1. And then we are again calculating the activation of the third layer, which is the final layer. So final layer, we know we have only 10 neurons. And for calculating the final layer, we are multiplying the weights with the activations of the second layer. And whatever the input activation, which is nothing but whatever the input image, whatever we have flattened, and we have added the bias neuron. And then the second layer activation neurons and the third layer activation neurons, we are returning. So this is our forward propagation step. So as you can see, this is the output. As you can see, the input neuron, as you can see, it is a 784 1D array, and last element is 0. And last element is 0.5. And this is the second layer neurons. So this is 51 image, 51 values. And this is the last layer, which has 10 values. So this is the cost function. So this cost function and the gradient checking, I didn't have much of success here. Somehow this is not giving the accurate value when I am using it for testing purposes. But you can do some modifications and get it working. So I'll just skip this. I'll just give a brief. So in the cost function, what we are doing is we are just using this formula to calculate the cost of it. And then in gradient checking, what we are doing, we are taking an epsilon value and we are checking the gradient manually. So as I've already explained in gradient checking video, the cost function with plus epsilon and minus epsilon, for that, whatever the weight we have to calculate the gradient, we just subtract it and divide it by 2 into epsilon. But this way of calculating the gradients is costly. And that's why we follow the backpropagation way of calculating the gradients. So whatever the backpropagation gradients we calculate, we can cross-check with this gradient and where they are closely matching. So for me, for a small test data set, this gradient checking is matching. But when I take a large test data set, train data set. So for a large train data set, this gradient check is not matching with the backpropagation gradient. But for a small train data set, it is matching. So that is still a work in progress. So this is a cross-validation function. So what we do here is, say, next we look at the cross-validation function. So whenever we do backpropagation, and for every iteration, whenever we are updating the weights, we just want to visualize how our backpropagation is performing. And for that, what we do is we run this cross-validation. So we'll just see out of a given set of test data, how many the weights are resulting in correct hypothesis. So in simple terms, whatever the weights we are calculating at each iteration of backpropagation, we'll just use them to cross-validate with the test data and whether it is improving or not. So this is not a correct way to look at it. But for me, since gradient checking and cost function way of checking whether back propagation is working fine is not working due to some issue. I'm relying on this cross validation to see whether my back propagation is working fine or not. If this doesn't work fine, what we do multiple parameter tuning. So that I will explain in the next video. Next, we look at the cross validation function. So whenever we do back propagation, and for every iteration, whenever we are updating the weights, we just want to visualize how our back propagation is performing. And for that, what we do is we run this cross validation. So we'll just see out of a given set of test data, how many the weights are resulting in correct hypothesis. So in simple terms, whatever the weights we are calculating at each iteration of back propagation, we'll just use them to cross validate with the test data and whether it is improving or not. So this is not a correct way to look at it, but for me, since gradient checking and cost function way of checking whether back propagation is working fine is not working due to some issue, I'm relying on this cross validation to see whether my back propagation is working fine or not. If this doesn't work fine, what we do multiple parameter tuning. So that I will explain in the next video. Next, we'll look at back propagation. Since we have training data of 60,000 size we have, and directly iterating all through all training samples is costly. Even it won't come out, the result won't come out in a reasonable amount of time. So what I am doing is I'm just taking the training samples in batches. So this is how I'm using. So I'm just taking the 200 samples, first 200 samples, then calculating the gradient and then updating the weights and then going for the next 200 samples. This way I'm iterating till 240 times. In other words, it will come till 200 multiplied by 240. So 48,000 training samples I'm doing, but the way I'm doing is 200 at a time. So this is another way of doing it. So this is called stochastic gradient descent. So if we start going through all the training samples and update the weights, it will take a lot of time and computing power. Even in regular machine learning problems, they follow the stochastic gradient descent, even though they have if they have small training data set, they'll just iterate or they'll just go through all training data set. But if they have a large training data set, then they use this stochastic gradient descent where they split the training data and then run one batch at a time and update the weights and check if it is performing fine. And this is the learning rate. So learning rate I have put as 1, and this is the cross validation data. So for whenever we iterate and update the weights, I'm doing a cross validation test to see out of 100 test samples, how many test samples it is iterating accurately. So it will help me in knowing whether my back propagation training is going in the correct way or not, because this takes time. So looking at this cross validation data, I can stop the training in between if it goes haywire. And this XP and YP, this is for plotting the cost function. But since cost function is not working fine, I just commented out the code. You can uncomment it and try out if you want. And this is the iteration. So 240 iterations, and for every iteration, I'm updating the weights. And for every iteration, I'm going through 200 training samples. So initially I'll go between 0 and 200, then 201 to 400, like that. And then I'm using the forward propagation to get the activation neurons for all the 3 layers. And then I'm calculating the error of the fine layer. Error of the fine layer is nothing but the final result, which is from the training result we get. I'm just putting the classes. So it will be 10 class. I'm just taking a 10 neuron, which initialized with all zeros. And then whatever the result is there, that I'm initializing it to 1. And since there is a sigmoid activation for the last layer as well, we get values between 0 and 1. So it won't cross the 1. So this final result, it will help us in subtracting and getting the correct error. So this is the error in the final layer. And since we only have one hidden layer, so we just need to calculate one more error layer. So these are errors in the hidden layer. So we multiply with the weights multiplied by transfer derivative of that particular layer. So this is a transfer derivative of sigmoid, which is nothing but whatever the sigmoid gives output, you multiply that with 1 minus that value. And then we calculate the theta delta. So this is we are doing for each training sample. So for every weight, we calculate the weight multiplied by the error in the corresponding neuron to which it is feeding. So this way we get theta delta values for all the weights. And next, again, second time, we again go through the next training sample. This way we go through 200 training samples. Once complete all the, we get the theta delta value. We know this theta delta value is for 200 samples. So here for the calculating the gradient, we do 1 by batch size of theta delta values. And we also add the regularization parameter. But since regularization, we have to ignore for a biased neuron. And one more important thing I forgot to tell is biased neuron I am adding in the end. So whatever is since you have 785 neurons, starting from 0 till 784, we'll have the neurons. So in the input layer, 784th neuron is the biased neuron. So for the biased neuron, which is 784th neuron, I'm putting p lambda equal to 0, so that just p lambda is just some temporary parameter. Ignore it. So that for regulation won't be there for the last biased neuron. And even for the second layer as well, the biased neuron will be in the end. And this lambda n is a regulation parameter. So lambda I'm taking as 1 and multiplied by the weight. So whatever the gradient is there, we'll just do the old school gradient descent, which is nothing but weight subtracted with learning rate times the gradient. This way we'll update the weights. And for every iteration, what we are doing is we are doing a cross validation. Since updated theta values will be available to the hypothesis function, since this is a global variable, so it will cross validate. And if cross validation crosses 95%, I'm stopping the training because there is no point in training more. And with limited resources, getting more than 95% is okay, because it's possible for the MNIST dataset to get 99% accuracy as well, but without using any third-party libraries while doing it from scratch, it's difficult to get. So I'm just taking about 95% accuracy is good enough. So as you can see, I'm just printing out theta values in between to see how they are getting updated. So for me here, you can see in this iteration, it will cross the 94, 95. So out of 100, 95, 95, I think it crossed 95% here and it stopped the training here. As you can see how the weights are updated. I'm just printing some weights here so that we can see how they're getting updated through each iteration. So once we got the 95% accuracy, I ran a final validation test. Ignoring the first 100 samples, I'm just taking the test data from 1000 to 2000 samples, and out of 1000, I got 853 correct. That means around 85% accuracy. So since running this back propagation and all is time taking, I'm just showing you the output. And one more thing is, you can stop this back propagation in between, again start it, because it has the updated theta values stored in this itself. It will again start fresh. So I have to run it, even though it is 240 iterations, I ran it 240 times once. After all the iterations got over, it is showing around 70 to 80% accuracy. Then again, I restarted the back propagation. Again, it ran till now, I think around 130, yeah, around 133 times it ran. Now it got 96% accuracy. And this is the final validation test. And here we can test out our whatever our neural network model is there. Whatever the weights we have calculated, we can test out those weights. So I'm just taking the 5003 sample, and we are printing the neural network output, which is 8, which is matching with this value. I'm just showing the image as well, whatever the test image. So let's just take, say, randomly some 6013 test data, and let's just run it. So it is 4, test accuracy calculated is 4. So 6014 we will try. So it is 2, it has accuracy calculated as 2. Okay, 6015 we will try. 0 and it is accurate calculation. But for some, it might go wrong, because we have seen out of 1000, only 853 it is able to predict properly. But anything getting above 80% accuracy is good enough in neural networks. So that's it for today's video. Thanks everyone for watching the video till the end. I know it's a lengthy video, but it is required for better understanding of neural networks. In the next video, I talk about the problems I faced and how I overcame them while tuning these parameters for the neural networks. Thank you.